Welcome everybody. Today's lesson has to do with titrations. Titration is an analytical technique in which you can calculate the concentration of a solute in an unknown solution. You're going to notice there's a few diagrams here at the bottom, and when you set up a titration, one of the key things is to use a component known as a burette. You can see the burette right over here. And what you want to do is you want to put a solution there with a known concentration. Usually we use a strong acid or a strong base, depending on what you're trying to titrate. Now, the bottom is an Erlenmeyer flask, and this is usually the solution where you're trying to find the unknown concentration. A lot of times this is referred to as the analyte. Usually the goal is to figure out through the titration what is the concentration of that unknown solution. Now the solution that goes in the burette, we refer to that as the titrant, and again you want to use something with a known concentration. When this titration apparatus is set up, one of the best things to do is to titrate an acid in a base, which is a neutralization reaction. And the goal is to use an indicator that will change color. Now, the example you're looking at here is an indicator known as phenolphthalein. And phenolphthalein is clear under acidic conditions. Once you start adding base, as you can see here, base is being added, sodium hydroxide is inside the burette. The solution will eventually turn pink. The minute it turns pink, you stop the burette and you measure the volume that it took to titrate this solution. Under basic conditions, phenolphthalein, our indicator, turns pink. If you look here, the known solution which goes in the burette, known as the titrant, is called a standard solution, and we're going to use that standard to determine the unknown concentration of the solution inside the Erlenmeyer flask. That solution, again, is called the analyte. Now, you will continue to titrate until you reach what is called the equivalence point. At this point, you know you've reached it when the indicator changes color and stays at that new color. In our example, we were adding base to acid, so phenolphthalein turned from being clear to pink. The equivalence point is a very important definition because at that point, the moles of the acid are equal to the moles of the base, and you can do a calculation, as you could see at the top here of this flow chart, that involves solution stoichiometry to figure out the concentration of the unknown solution. Here's an example. According to this, we are using 0.1 molar NaOH solution. According to this equation, it took the experimenter 48.6 milliliters to titrate an unknown hydrochloric acid solution, and in that solution we had 20 mLs. Now you could see the reaction right over here. The acid plus the base gives you salt and water. This is a classic neutralization reaction. Now I'm going to diagram what is happening here. You see, the analyte, which is in the Erlenmeyer flask, this is where the HCl is. According to this, we do not know the concentration. We're looking for the molarity. What we do know is that we put in here 20 mLs of hydrochloric acid solution. Now, the burette is where you put the known solution. Here's a little stopper. You're going to put here NaOH, and according to this, we put 0.100 molar was our concentration. So remember, we add an indicator in here, 1 or 2 drops, and you're going to start to titrate and as the drops fall in here, you're going to measure the volume that it takes from the start to the end, and you're going to calculate how much milliliters it took to neutralize this solution. According to the equation, it took 48.6 milliliters to titrate this. Now, once we have this information, here is how we're going to figure out this problem. Remember that when you do stoichiometry, molarity times volume gives you moles. We want to always convert our information into moles. Well, the molarity of the given is 0.1. Now remember, the volume has to be changed to liters. So if we change 48.6, it'll become 0.0486 liters. If we multiply the molarity by that volume, just like this, we're going to convert that into moles. And this is going to be how many moles, let me fix that, how many moles we have of the given. The given in this case is NaOH. Now, if you recall from the previous problem, the mole ratio, okay, because this is the given, this is the unknown. We're trying to find the concentration of the unknown solution. Notice the mole ratio, B over A, is 1 to 1. So if we get the moles of the given, and we multiply that by the mole ratio, the number won't change. The mole ratio is a 1 to 1 ratio. So we still get moles of B. B in this case is HCl. Well, the last thing we're going to do here is we want to find the molarity of HCl. Now remember that molarity is equal to moles over volume in liters. Well, we just found the moles, because at the equivalence point and through the mole ratio is a 1 to 1 ratio, so we have 0.00486 moles of HCl. Now we got to convert the volume of HCl into liters. That'll be 0.0200 liters. So if we divide by 0.0200 liters, we're going to get a molarity, and I'll write this right up here, of 0.243 m for molar. That would be our answer to this problem. Now we can check this. If you look here, here's the equation. Here is the, they're converting the volume from milliliters to liters, okay? And if you multiply the volume by the molarity, there's the moles of the given, of A. There's the mole ratio, 1 to 1. This is the moles of B. And then over here, molarity, or moles, divided by the volume in liters. They changed it to liters over here by dividing by 1,000. Gives you the answer that we got. So we were able to determine the concentration of the unknown solution, which was HCl. Now let's try this. Let's try a couple of practice problems. First practice problem: what is the molarity of an HCl solution if 27.3 milliliters of it neutralizes 134.5 milliliters of barium hydroxide with a concentration of 0.0165 molar? The first thing I would do is, let's write the equation. HCl is reacting with barium hydroxide. So there's your acid. Here is your base. You're going to make salt and water. The salt here would be barium chloride and water. Make sure we balance this equation. You need to put a 2 here to balance the hydrogens and the oxygens, and a 2 here. So according to the question, we want the molarity right over here of HCl. So we're going to call this B, our unknown. So we're looking for the molarity. We are given the volume. So we have 27.3 milliliters of this guy. The given is barium hydroxide. So we'll put A over here. And according to this, we have the molarity. It's 0.0165. We also have the volume, which is 134.5. And remember that when we do solution stoichiometry, molarity times volume in liters gives you moles. So let's change this to liters. This becomes 0.1345 liters. And let's go ahead and multiply the molarity of the given, which is barium hydroxide, 0.0165, and we're going to multiply that by 0.1345 liters, and we're going to get 0.002219 moles, and this is going to be moles of the given, which is barium hydroxide. Now notice here the mole ratio is not 1:1. Look at B over A. Here's B, here's A. The mole ratio here is 2/1. So when you multiply the moles of the given by 2, you're going to get 0.0044385, and this is moles of B, which is HCl. Okay? Now we want the molarity like in the previous problem. So if you recall, molarity is equal to moles, which we just found, and then we're going to divide that by the volume in liters. So we got to convert this volume also into liters. That'll be 0.0273 liters. Just divide by 1,000 to go from milliliters to liters. And when we divide by 0.0273 liters, we're going to get our answer. I'm going to use 3 significant figures. All our numbers have 3. And we end up getting 0.163 molar as our answer. And if you look at choice C, there is our answer in this multiple choice problem. Okay? Now we got one more. Practice exercise number 2. This time we want the molarity of NaOH solution if 48 milliliters neutralizes 35 mLs of 0.144 molar H2SO4. Again, let's set up the equation. We have sodium hydroxide reacting, that's a base, a strong base, reacting with sulfuric acid, which is a strong acid. According to this, we want the molarity of NaOH, so we're going to call this B. We're looking for this. So we want the molarity. They do tell us that the volume is 48 milliliters. And we want to know, it neutralized this given information here. They give you the concentration of sulfuric acid at 0.144 molar. They also give you the volume. We'll change that to liters in a minute. And we're going to do a similar solution stoichiometry problem. Now remember that when when an acid and a base react, we're going to make salt and water. The salt here is going to be Na2SO4, which is sodium sulfate, and we're going to also make water. So here we're going to put we're going to need to balance. There's 2 sodiums on the right, so I'm going to put a 2 here. Then I'm going to need to balance those hydrogens. There's 4 on the left, so I'm going to put a 2 here, and that actually balances out everything. So remember, the first step in solution stoichiometry, if you get the molarity and the volume in liters, you can convert it to moles. So here, I'm going to change this. I'm going to divide by 1,000. That'll be 0.035 liters. So let's do the first step. Let's get the molarity of the given, 0.144 molar. Let's multiply it by the volume, which we just changed to liters. And we're going to get 0.00504 moles of the given, which is sulfuric acid, H2SO4. Now, let's multiply by the mole ratio. Notice it's B over A, is a 2-to-1 ratio. There are 2 moles of NaOH for every 1 mole of H2SO4. So it's a 2-to-1 ratio. So when you multiply the given by 2 there, you get 0.01008, and that will be moles of the unknown, which in this case is NaOH. Now, the last step is they want the molarity. Well, we got everything we need. You see, molarity is going to be the moles, which we just got, divided by the volume in liters. So we got to change 48 milliliters into liters. That'll be 0.0480 liters. So we're going to divide by 0.0480 liters, and then we're going to round this also to 3 significant digits, and we're going to end up getting 0.21 with a 0 here at the end and a capital M for molarity. And the answer to this problem is the concentration of NaOH is 0.210. Okay? So these are examples of using titrations, but the math is the same as you do when you're performing solution stoichiometry types of problems. Okay? And that'll conclude our lesson.